All right, let's dive right in. Today, we're going to take a peek behind the curtain at the hidden world that makes up, well, everything. We're talking about the secret lives of particles and how their little dances create the solids, liquids, and gases we see every single day. So let's get into it.
So, think about this for a second. An ice cube, a puddle of water, and a cloud of steam. On the surface, they seem completely different, right? One's hard, one's sloshy, one you can barely even see. But here's the kicker. They are all just different faces of the exact same thing, water. The secret isn't what they're made of, but how the tiny, tiny particles inside them are behaving.
And it turns out there's this one fundamental rule, one core idea that explains not just water, but all the matter in the entire universe. If you can get your head around this one concept, you've basically unlocked the secret code for understanding solids, liquids, and gases.
And this is it, the kinetic theory of matter. It sounds fancy, but it's actually super simple. It boils down to three things. 1, everything is made of tiny particles. 2, those particles are always moving. They never stop. And 3, and this is the most important part, the more energy they have, the more they move. Just remember that. Energy is the boss. It dictates motion, and that motion is the state of matter.
Okay, so we've got our rule book, the kinetic theory. Now let's see how it actually builds the three states of matter that make up our world. We'll start at the bottom with the lowest energy and work our way up. First up, solids. And the first thing you notice is just how incredibly neat and tidy they are. These particles have the least amount of energy, so they're locked into this tight, repeating, almost crystalline pattern. You can think of them like soldiers in a marching band, standing in perfect formation. They can't just wander off, but they can kind of jiggle or vibrate in their spot.
And that locked-in structure, it explains everything we know about solids. Because those particles can't leave their posts, a solid has a fixed shape and a fixed volume. You can't just squish it. And since they're packed together so tightly, solids usually have a really high density. It all flows directly from what those tiny particles are doing.
Okay, now let's start adding some energy. Let's turn up the heat. Those vibrations get more and more intense until, snap. The particles break free from that rigid structure. And boom, you're in the liquid state. The marching band is over, now it's more like a crowded dance floor. Everyone's still packed in close, but now they can move around, sliding and flowing past each other. And that new freedom to move is exactly why a liquid can flow and take the shape of whatever you pour it into. But notice how the particles are still touching, they're still right next to each other. That's why liquids, just like solids, have a fixed volume. You can't really compress them. Their arrangement is all jumbled up, but there's still a tight-knit group.
All right, time to crank the energy dial all the way to max. Now the particles have so much energy they completely escape from each other's grasp. Welcome to the gas state. Forget the dance floor, this is like a room full of bouncy balls that have had way too much sugar. They are super far apart and they're moving incredibly fast, like 500 meters per second fast, zipping around randomly in every direction. With all that chaos and high-speed motion, a gas has no fixed shape and no fixed volume. It just expands to fill whatever container you put it in, no matter how big. And all that empty space between the particles? That's why gases have such a low density and why they're so easy to compress. You're basically just squeezing out the empty space. So here's a quick summary that puts it all together. You can clearly see the story here. As we add energy and go down the table from solid to liquid to gas, everything changes in a predictable way. The density drops, the tidy arrangement gets messy, and the movement goes from a little vibration to total freedom. It's a perfect progression. But of course, things don't just stay in one state forever, and this is where the story gets really dynamic. Matter is always on the move, transforming from one state to another. Let's get into the art of that transformation.
Think of this picture as our roadmap, and the most important thing on this map is that big green arrow on the side. It says energy, because that's what drives everything. You put energy in, and you move up the ladder, from solid to liquid to gas. You take energy out, and you move back down. It's that simple.
So let's take a quick trip around this map. You start with a solid, you add energy, and it melts into a liquid. Then you give that liquid even more energy, and it boils into a gas. Now let's go the other way. You take a gas and cool it down, you're removing energy, and it condenses back into a liquid. Remove even more energy from that liquid, and it freezes back into a solid. See? A perfect cycle. Now you might have noticed the word evaporation on that map, and you might be thinking, isn't that the same as boiling? Well, not quite, and it's a really important difference. Boiling is like a big, dramatic party that happens everywhere in the liquid at one specific temperature. Evaporation, though, is much quieter. It only happens at the surface, and it can happen at almost any temperature, as the fastest particles just decide to escape. Okay, check this out. This graph, called a heating curve, tells a fantastic story. Along the bottom, we're adding heat. Going up the side, we're tracking the temperature. So we start with a solid, and as we add heat, the temperature goes up, up, up. And then something weird happens. The line goes totally flat. That's melting. Once it's all liquid, the temperature climbs again until, whoop, it goes flat again. That's boiling.
And this right here is probably the most mind-bending part of this whole story. During those flat sections, while it's melting or boiling, you are pumping tons of energy into this thing, but its temperature does not change one bit. So where's all that energy going? It's not making the particles move faster. It's being used for one job and one job only, to break the bonds holding the particles together. It's transformation energy, not heat energy. So cool.
And just to show you the whole picture, the process works exactly the same in reverse. This is a cooling curve. It's a perfect mirror image. As a gas cools down and turns back into a liquid, or a liquid freezes into a solid, it releases all that stored energy, creating the exact same flat spots at the exact same temperatures.
Okay, so we've got all this particle theory down. But what's the point? What are the real-world consequences? Let's zoom in on gases, because that's where you can see the effects of all this most clearly. Ever wonder how a hot air balloon works? It's pure kinetic theory. When you heat the air inside, those little air particles get a huge boost of energy. They start moving faster and smashing against the inside of the balloon way harder. This pushes the balloon fabric outwards, making the whole thing expand. Now you have the same amount of air in a much bigger space, which means it's less dense than the cool air outside, and up it goes.
That outward push we were just talking about, that's what scientists call pressure. It sounds like a complex idea, but it's really not. It's just the grand total of trillions and trillions of tiny gas particles constantly smacking into the walls of their container. That's it. That's pressure.
And that gives us a really simple relationship. If you take the same number of those zippy gas particles and you squeeze them into a smaller box, they've got less room to roam. That means they're going to crash into the walls way more often. More crashes per second means, you guessed it, higher pressure.
And you've totally used this principle in real life. Think about a bicycle pump. When you push down on that handle, what are you doing? You're decreasing the volume, forcing all that air into a smaller space. The pressure skyrockets, getting so high that it can force its way into your tire. It's a perfect, everyday example of particle theory in action.
So let's circle all the way back to that fascinating heating curve and end with this one final thought. Imagine you have a glass of melting ice. You can stick a thermometer in there and it will read 0 degrees Celsius. You can put it over a flame, pump heat into it, and it will stay at exactly 0 degrees until every last sliver of ice is gone. So, if the energy isn't making things hotter, where is it going? It's going into the invisible work of breaking bonds, of literally changing the world from one state to another. Pretty amazing when you think about it.